Hi friends, in the last lecture we defined topological spaces, what are known as discrete and indiscrete topologies, and metrizable spaces. Right. Now in this lecture we will define what are known as strong and weak topologies, and we shall prove theorems associated with this topic. Okay. So without further ado, we shall jump on to the definition for strong and weak topologies. Definition. Strong and weak topologies. So let's X be a non-empty set. And τ1 and τ2 be two topologies on X. Then the topology τ1 is said to be weaker than the topology τ2 if τ1 is contained in τ2. Okay. Alternatively, T2 is then said to be stronger than τ1 is said to be stronger than τ2 is said to be stronger than τ1 and is denoted as τ2 contains τ1, the superset notation. Okay. So if τ1 and τ2 are two topologies on a non-empty set X, then τ1 is said to be weaker than τ2 if τ1 is contained in τ2. Okay, that is all elements in all the subsets of X which are in τ1 can be found in τ2. Okay, and it can also be said in this way, like τ2 is then said to be stronger than τ1. Okay, it can also be said in this way, and is denoted as τ2 contains τ1. This superset notation, τ2 as a superset of τ1. Okay. Next, we have a theorem associated with this topic concerning strong and weak topologies. So the theorem goes like this. Let X be a non-empty set set of all τy such that I element of I be a family of topologies on X. And that τ equals intersection over I element of I, τ I. Okay, τ equals the intersection of all the elements in this family. Okay, then we have the following two statements. What are they? Then τ is a topology on X which is weaker than each τy for I element of I. Okay. And 2, if script U is any other topology on X any other topology on X which is weaker than each τy, then τ is stronger than U. That is, τ contains U, right? I.e. τ contains U. So the theorem says that if X is a non-empty set and we have a family of topologies, tau I, such that I identify on X, and we define tau to be their intersection, then this intersection, right, will be a topology on X, and this intersection, right, it will be weaker than each member of this family. And now, for the second statement, if use any other topology on X, which is again weaker than each tau I, then tau is stronger than U. That is, tau contains U. Okay, I hope that's clear. So we prove the theorem. So we shall prove the theorem. So to prove the first statement, first we need to show that tau is a topology on X, which is weaker than each tau I, right? So to do that, we need to first show that tau is a topology on X, right? We first need to prove that tau is a topology on X, then we need to show that tau is weaker than each tau I for each I. Okay, so first we shall show that tau is a topology on X. We shall first prove that tau is a topology on X. Okay, how do we do that? We need to show that the empty set phi and X are members in tau, then tau is closed under arbitrary union, and tau is closed under finite intersection, right? So first we shall show that phi and X are elements of tau. To prove that phi and X are elements of tau, how do we do it? Since now tau equals intersection I element of I tau I, remember that. So since each tau I is a topology on X, what? The empty set must be a member of tau I, right? Phi element of tau I for all I element of I, right? This implies phi must belong to their intersection, right? See, if phi is an element of tau I for all I, then phi must belong to their intersection, right? And what is this? This is nothing but tau, right? That is phi element of tau. Next we shall, again, we can prove X element of tau in a similar fashion, right? Since each tau I is a topology on X, since each tau I is a topology on X, what? X element of tau I for all I, element of I, right? Which implies X element of intersection I element of I, tau I equals tau. That is X element of tau, right? So we proved that phi and X are elements of tau. So next we shall prove that tau is closed under phi intersection. Okay. Still proving statement 1. Still proving statement 1. I shouldn't have wrong that. So next we shall prove that tau is closed under finite intersection, right? To prove that tau is closed under finite intersection. How do we do it? Take any finite number of open sets A1, A2, etc. AN in tau, right? We need to prove that their intersection also belongs to tau, right? So let us take A equals intersection J element of I, AJ. Okay? We need to prove that. We need to prove that A element of tau, right? So how do we do it? We need to prove that A element of tau. Now, since tau equals intersection I element of I, tau I, what does this imply? Each AJ, right? Each AJ must belong to what? Tau I for all I element of I. Why? We're taking Aj in tau, right? And since tau equals the intersection, each Aj must belong to, all the tau i's, right? Because tau is actually the intersection of each of these tau i's, right? So each Aj must belong to every tau I, right? So now since each tau I is a topology on X, what? It must be closed under finite intersection, right? Since tau I is a topology on X, it must be closed under finite intersection. Which implies intersection J element of I, Aj must belong to tau I for all I, right? Now what is intersection Aj? It's nothing but A, right? Which implies A element of tau I for all I element of I, right? Now if A is an element of tau I for all I element of I, this implies A element of intersection I element of I, tau I. Now this is nothing but tau, right? Tau. That is A element of tau. Therefore, tau is closed under finite intersection, right? Next we shall prove that tau is closed under arbitrary union. Arbitrary union, okay? Take any arbitrary, so take any family B1, B2, B3, etc. Family of an arbitrary number of open sets in tau, right? We need to prove that their union is also member in tau, right? So let's B equals union over J element of I, Bj. Okay, we need to prove that B is an element of tau, right? How do we do it? Now, since tau equals intersection I element of I, tau I, each Bj must belong to every tau I, right? Each Bj, therefore, each Bj must belong to tau I for all I element of I, right? So Bj, okay. Each Bj must belong to tau I for all I element of I, which implies what? Bj must belong to, intersection of Bj, right? Intersection Bj must belong to tau I for all I element of I. Why? Since tau I is a topology on X. So, and must be closed under arbitrary intersection, finite intersection. So, what is intersection Bj? This is B, right? That is B element of tau I for all I element of I, right? This implies B element of intersection I element of I, tau I, right? Since B is an element of tau I for all I element of I, right? If B is an element of every tau I, then B must belong to their intersection, right? And this is nothing but tau, right? That is B element of tau. Therefore, tau is closed under arbitrary union. So we have proved that. Hence, tau is a topology on X, right? We have proved all the three conditions, right? Therefore, tau is a topology on X. Next, it remains to prove that tau is weaker than each tau I, right? So, we have tau equals intersection I element of I tau I, right? What does this imply? This implies that tau is contained in tau I for all I element of I, right? See, tau is nothing but the intersection of tau I, right? So I'll just represent it here. I'm just going to draw a number of tau i's here. Suppose this is tau 1, this is tau 2, tau 3, tau 4, etc. And their intersection would be this small area, right? And this small area is contained in each tau I, right? See, this one is contained in tau 1, this one is contained in tau 2, this one is contained in tau 3, and this one is contained in tau 4. So, this is tau, right? This is tau. So, tau is contained in tau I for all I element of I. That is, tau is weaker than each tau I. Pretty straightforward, right? Next, we should prove the second statement, which states that if U is any topology on X, which is weaker than each tau I, then tau is stronger than U, right? So, to prove the second statement, we are given the condition that U is a topology on X which is weaker than each tau I, right? That is, U is contained in tau I for all I element of I, right? Let's use a Venn diagram to for better clarity. So U is contained in tau I. So let's take a number of tau i's here. Say tau 1, tau 2, tau 3. Okay, for simplicity, let's just restrict the number to 3. Okay, so tau 1, tau 2, tau 3. So this is intersection tau I, right? This small area. I'll just magnify it here, somewhat like this area, right? Now, if U is contained in tau I for all I, then U must belong to this area, right? U will be some area within this area, this intersection area, right? So, U can be any size restricted by this area, right? It could be like this, okay? U. And this is intersection tau I. So this implies what? U is contained in intersection I element of I, tau I, I element of I, tau I, right? This implies that tau is stronger than U, right? So that's all the theorem. So now we have a corollary to the theorem following this. The corollary goes like this. Let X be a non-empty set and script D be a family of subsets of X then there exists a unique topology tau on X which is the smallest topology on X, which is the smallest topology on X containing D. So the corollary states that if we have an empty set X and a family of subsets known as D or notated as D, then there exists a unique topology tau on X, which is the smallest topology on X containing D. So we should prove the theorem now. How do we go with this? We consider a collection. Right, we consider a collection of topologies. Okay, consider a collection of topologies. What kind of topologies? Those topologies containing D. Okay, consider a collection of topologies on X containing the family of subsets D. Okay. Clearly, this collection is non-empty, right? Because there is a discrete topology which obviously contains D. So it is non-empty, right? Clearly, it is non-empty. Since it contains a discrete topology which contains D anyway, right? Now we take tau. Tau, we define tau to be the intersection of all the members in this collection. Okay, so let tau be the intersection of all the members in this collection. Then applying the theorem which we proved just now, what do we get? Tau is a topology on X, right? Then applying the previous theorem, we get tau is a topology on X. Moreover, tau contains D, right? Moreover, tau contains D and is also the smallest topology on X containing D. Because if if there is any other topology on X containing D, it is clearly a member of this collection, right? And that member will obviously be stronger than its intersection, right? We just saw in the last theorem, right, that intersection is like much weaker than any other sets contributing to that intersection, right? So moreover, tau contains D and it is clearly the smallest. It is the smallest topology containing D, since any such topology on X containing D will be a member of this collection, right? And hence will be stronger than tau. Hence will be stronger than tau. Moreover, the uniqueness of tau is also trivial. Okay, the uniqueness of tau is trivial. So our theorem is proved. Also, the topologies so generated, so obtained by through this definition, are then said to be generated by this family D. Okay. So our theorem is proved. That's the proof. So thanks for watching.